So in a one-way ANOVA, we had a quantitative variable that we were trying to predict and a single categorical predictor. So we had a quantitative response and one categorical variable predictor. We might have had three different levels of that categorical variable, but it was just one categorical variable. So what happens if we want to consider the effect of two categorical predictors? This will be the topic of a two-way ANOVA. So we have a model for these. We had a model for the one-way ANOVA as well. Our response Y is some average, baseline average, plus the effect of factor A, plus the effect of factor B, plus any interaction between the two, plus the errors. In a two-way ANOVA, we're going to want to be in this situation. We're going to want a factorial experiment. That is one where each combination of treatment levels occurs. We want it to be balanced. We want each combination of treatment levels to have the same number of observations. We also want replications, the number of replications to be greater than 1. Fixed effects are when we pick the effects that we want to look at. These are the particular treatment levels that we are concerned about. So here's a picture of a two-way ANOVA setup. Let's say that we have 3 levels of factor A and 4 levels of factor B. We can picture that A1, B1, so every combination of treatment levels is hit, right? A1 with B1, A1 with B2, A2 with B1, A2 with B2, etc. And it's replicated, meaning there's more than one observation in each of these cells. Okay, in a two-way ANOVA, we are interested in the effects of 2 factors, the main effects. Null hypothesis for the main effects is that the means for all factor levels are equal, and the alternative is that at least one's different. So there's not much new there. However, when the 2 categorical variables contribute more than an additive effect, we have what we call an interaction. The null hypothesis for the interaction is that the mean for the level of one factor does not depend on the level of the other factor. And the alternative hypothesis is that the mean for level of one factor depends on the level of the other factor. If the interaction is not significant, we're going to remove it and rerun the model without the interaction term. If the interaction term is significant, the change in one factor depends on the level of the other variable. Do not blindly interpret your main effects in the presence of an interaction. You could unfold your treatments and run a one-way ANOVA with all the treatment combinations as a single categorical predictor, or interpret the means depending on levels of the other variable. So this is an example of some plots that we might look at when we're thinking about interactions. So sometimes they're called mean plots because what we're doing is we're plotting, like this blue dot right here is the mean of level 1 for factor A and level 1 for factor B. So each of these dots represents the mean for each treatment combination. Here we only have 2 levels of factor B in these pictures and 3 levels of factor A, so there are 6 total treatment combinations. All right, so this top left picture is the one we're going to focus on right now. Notice how factor A, the means change. Level 1, they're generally higher. Level 2 of factor A, they're generally lower, and level 3, they're generally higher again. So it looks like factor A is significant here in this example. However, from the distance between the lines, the jump from level 1 of factor B to level 2 of factor B is not very evident. So it looks like factor B is probably not significant. And it doesn't look like the mean of one variable depends on the level of the other variable because these lines are parallel. So it looks like there is not a significant interaction. All right, the second plot on the top right, we can see that level 1, level 2, and level 3 of factor A, the means stay pretty much the same. So we're going to say it looks like A is not significant. However, this time, the means do change, it looks like significantly from level 1 of factor B to level 2 of factor B. So it looks like factor B is significant. Again, it looks like there's not an interaction. These lines are parallel. The level of one variable does not depend on what level of the other variable you're on. The change for B is the same no matter what level of A you're on. And that's what tells us it doesn't look like there's an interaction. Okay, down here on the bottom left, we're going to focus on this plot now. Notice that the means for A do look like they change according to what level of factor A you're on, so it looks like A is significant. It does look like there's a shift up from level 1 of B to level 2 of B, so it looks like B is significant. And again, it doesn't look like there's an interaction. These lines are pretty parallel, and what that means is that the shift, for instance, the change in the mean from level 1 to level 2 of B is the same no matter what level of the variable A you're on. So the change in that mean for factor B doesn't depend on what level of factor A you're on. All right, and the last plot is the last situation we can have. This one shows a strong interaction. This one, what factor B is doing depends on what level of factor A you're on. It's not always a shift up from level 1 to level 2 of B. It's a shift up for level 1 of A, but B has a shift down for level 2 of A, and it has a shift up for level 3. Those lines cross. They have an intersection, or they would cross if they kept going, and so it looks like there's a very strong interaction there. All right, so let's jump into an example. Arlington's is a general retailer that competes with discount and wholesale club retailers. 40 stores were selected and divided into 4 groups of 10 stores each. To each group, a different in-store sales location was chosen for mobile electronics, an in-aisle display, front of the store, kiosk, or expert. The chain also allowed mobile payment methods for these devices. For 5 of the 10 stores testing each location, 5 were assigned mobile payment options and 5 were not. Sales in thousands of dollars were recorded for each. So you can see a snapshot of our data right over here, and this is attached with your lecture notes so you can play along with R as we go. All right, so the first thing I did was ran an interaction plot in R. So the command for that is interaction.plot. The first variable here is the one that goes on the x-axis. The second variable is the separate lines on this picture, and the last variable is your response variable. Remember, we're trying to use location and mobile pay options to predict sales. So sales goes on the y-axis, it goes third in the interaction.plot call, and then location and mobile pay are your 2 predictors. I typically do the separate lines for the one with fewer categories, so mobile pay only has 2, so I chose that as my separate lines. Location has 4 different categories, so I chose that as my x-axis variable. All right, so what does it look like here in our interaction plot? Well, it looks like location is significant, right? We definitely see that you have a higher mean sales in the front of the store location, lower for expert, even lower for aisle, a little lower for kiosk, right? So it looks like location is probably significant. How about mobile pay? Yep, that looks like a nice jump in sales according to whether you offer mobile pay or not. So it looks like the top dotted line is mobile pay, and so it looks like sales in general are shifted up when you allow mobile pay. And it looks like the gain that you get from mobile pay is about the same no matter what location you're at in the store. And so that would indicate that there's not an interaction. It looks like it's just an additive effect. So, but let's check the numbers out, because you can just get an idea of what's going on with the interaction plot. The p-values are going to tell us the real story. So I've got my output here. Notice that I fit my model, and remember, when I fit a model in R, I'm almost always going to call it the object fit. Okay? I use my definition symbol, and I use my AOV function. The AOV function is for ANOVA. Again, your Y variable goes first, just like before. Tilde, your predictors. So we want to put in mobile pay plus location plus mobile pay times location. All right, so we have a row in our ANOVA table for mobile pay, a row for location, and a row for our interaction, and of course our row for residuals. But this interaction row is the one that we're going to look at because we want to see if that interaction is significant. So our p-value for the interaction is 0.747. So is that significant? No, that's a really large p-value. That's way over 0.05. So the interaction is not significant, so we're going to remove it and run the model again, leaving out this interaction term. Also notice the way that I put the interaction in. It's literally mobile pay asterisk location. It's mobile pay times location. All right, so I'm rerunning the model. I'm calling it fit again. I'm using my AOV. I've got my predicted variable sales here first, tilde mobile pay plus location without my interaction term. And we see that our p-values are very tiny for both mobile pay and location of display. These are both significant. They're highly significant. Those p-values are very, very small. So this confirms what we saw in the interaction plot. It looked like mobile pay gave us a good gain. It looked like location sales really did depend on location. And it looked like there wasn't an interaction. Our p-values confirmed this. But now we need to know exactly where the differences are and by how much. So we're going to run a Tukey's HSD again. So just the same way we did in one-way ANOVA, we use Tukey HSD of our fitted model. And it's going to spit out comparisons for the mobile pay variable and also the location variable. So it's telling us that no mobile minus mobile has a difference of negative 0.7175. It gives us a confidence interval for that, and it tells us that it's highly significant because our p-value is essentially 0. Same with location. It's going to compare all 6 pairwise comparisons: expert to aisle, front to aisle, kiosk to aisle, front to expert, and kiosk to front. All right, so let's take a look at this. First of all, let's notice that every single p-value for every single pairwise comparison is highly significant. They're all tiny. So all the differences are highly significant. And we can look at the interaction plot. We can see that average sales are highest when the display is in front of the store and mobile pay is enabled. But since there is no interaction, we can talk about these effects separately. Maybe this chain is really expensive to offer mobile pay, and maybe the actual amount they're gaining from it isn't worth allowing it. Even though it's statistically significant, maybe it doesn't, the profit margin is just not there for it. So it's nice when we don't have an interaction, we can talk about these effects separately, and we can tease out exactly how much we're getting by offering mobile pay and how much we're getting by putting it in the front of the store. So let's first look at the comparison of mobile to no mobile. So we see that no mobile minus mobile is negative 0.7175, and that difference is significant because the p-value is tiny. So no mobile minus mobile is negative, which tells us sales are higher for mobile. Because if you take two things minus each other and it's negative, the second thing's bigger. So offering mobile pay adds $717.50 in sales on average, and this difference is significant because of that tiny p-value. We could, of course, just interpret that confidence interval. We've got the lower and upper bound for a confidence interval for that difference. And we would interpret that we are 95% confident that sales are higher on average when adding mobile pay by between $538.30 and $896.70. Remember, we take no mobile minus mobile and get negative numbers. It means mobile's bigger by the positive amounts that are listed here. Okay, and we can also look at all the pairwise comparisons for the location. So I'm just going to look at all of the ones compared to the aisle location. I ran the interaction plot backwards. I put mobile pay on my x-axis and location as my separate lines, just so you could maybe have another way to picture what this variable is doing to sales. So notice here that aisle is the bottom line, expert is next, kiosk is next, and the front is the top line, right? So no matter whether mobile pay is enabled or not, the front of the store location is always higher than the other locations. So I'm just going to compare everything to the baseline, which is aisle. So compared to the aisle location, expert adds $485, kiosk adds $972, and aisle, or the front location, adds $2,104 in sales on average. So that's just 3 comparisons I chose to talk about. All right, so now that was an example of where we did not have an interaction in a two-way ANOVA. Now let's do an example where we do. So a credit card company tried different direct mailings for their customers. They offered either SkyWest miles or Use Anywhere miles, and either regular, double, or triple miles to their customers in a full factorial balance design, and they recorded the amount charged in the column called total. So when you pull up this data set, your CSV file, or look at it in R, it is very large. I think it has 30,000 rows. So definitely don't look at your whole data set. Just pull it in, and if you call it miles, for instance, then just look at like the first 5 rows of it. So 1:5, comma, inside your square brackets, and you can see the column names and how everything's labeled. Okay? All right, so I called that data set in. I'm going to fit my ANOVA model. My Y, my response, is called total.charge in R. I looked at the first 5 rows to determine that. Tilde, my predictors, the miles variable, the amount variable, and the interaction of miles times amount. All right, so this time we have a different story, right? Our interaction is highly significant. So we're going to have to think about things differently than we did on the last example. Now let's look at the assumptions real quick. It does look like there's little to no evidence that the errors don't have mean 0. It looks like the variance is about the same no matter where you are. And this looks fairly linear, and plus we have a really enormous sample size, so we can probably assume normality of the errors. All right, so the residuals versus predicted plot showed little to no evidence against the errors having mean 0, also against having equal variance. And the QQ plot is not totally linear, but I don't see it making a shape, so I'm going to say little to no evidence against normality of the errors. All right, so I've created the interaction plot both ways. The first time I put amount, regular, double, or triple, on the x-axis and made the lines the type of miles that were offered, Anywhere or SkyWest. And the second way I did it was by putting the miles, Use Anywhere or SkyWest, on the x-axis, and made the amount, regular, double, or triple, the different lines. Because sometimes it's easier for me to see things if I look at it both ways. Okay, so does it look like there's a significant interaction here? Yes, it does. It looks like on this plot, the gain that you get by offering Anywhere miles is definitely different depending upon whether you offered regular, double, or triple miles, right? It looks like those lines are not parallel. They would cross if you kept extending them. And we can see that interaction over here on the second plot as well. The jump from here to here is drastically different from there to there. Okay, and that's confirmed by the teeny tiny p-value in our output. Our interaction is highly significant. It looked like that on the interaction plots, and it was confirmed by our teeny tiny p-value. Because the interaction is significant, we cannot talk about the overall effect of amount, either regular, double, or triple, alone, but we need to discuss this at different levels of types of miles, Use Anywhere and SkyWest. All right, so I did a Tukey's HSD of my fitted model, and I looked at all the pairwise comparisons. And now we have interactions. So we have to look at Use Anywhere coupled with double minus SkyWest coupled with double. We had to look at all the pairwise comparisons with all of the terms that interact with each other. So I put these in garnet because we're going to talk about those in just a second. And then I put the other ones, another couple comparisons, in just black bold because I'm going to talk about those separately. Notice that my use anywhere triple miles, let's take a look at what those are in. That's in my black bolded comparisons here. My use any comparison with use anywhere triple compared to any other combined offer, compared to SkyWest double, use anywhere double, SkyWest regular, use anywhere regular, and SkyWest triple, are all highly significant. Okay, you see that? So use anywhere triple is significantly different from all other combinations. Now, this is something called homogeneous groupings. We're going to see that use anywhere double, SkyWest triple, and SkyWest double are not statistically significantly different from each other. So let's take a look at that. If we look at any comparison with use anywhere double, SkyWest triple, and SkyWest double, so use anywhere double to SkyWest double, SkyWest triple to SkyWest double, and SkyWest triple to use anywhere double, you can see that these are not statistically significant. And so those three we're going to call a homogeneous group. They are not statistically different from each other. And we would see that SkyWest double is not statistically different from use anywhere regular. So SkyWest, let's see, SkyWest double. So SkyWest is the bottom line and doubles here compared to use anywhere regular. So the top line at regular, it's saying that those are not statistically significantly different by putting those in a group. And then use anywhere regular to SkyWest regular. Now there is a way to get the actual means for your mean plot out of R. It's in your R help file. But we've listed them here. The use anywhere triple average of that combination is 1732.21. So use anywhere and triple is right here. And that point is 1732.21. Let's look up the value for SkyWest triple, 1484.34. So if I wanted to, I could label all of these exact means by recording them, but I just wanted to show you how you find them. So from double miles, triple miles for SkyWest didn't increase amount charged significantly. So if you look on your interaction plot, you'll see what I'm talking about here. For double miles, so we're right here, triple miles for SkyWest didn't increase amount charged significantly, okay? So if you go from double to triple on SkyWest, it didn't increase significantly. But triple miles for the use anywhere generated a much bigger gain, an average of $205.28 more in average charges on the credit cards. It's the combination of triple miles and use anywhere miles that makes a difference. And we could see that just because it was the highest mean and it was significantly different from all other groupings. Okay, so having an interaction complicates things a little bit. You just might need to write more and think a little bit more about what you're saying. So if we only have one observation, we've got other topics that we need to go over now. If we only have one observation per factor level combination, we cannot test for an interaction. This happens when repeating factor level combinations is not practical or is too expensive, but it's not optimal. So your book will cover designs that are not replicated, but I typically don't use any examples with it. The only thing you really need to know is that you cannot test for the interaction, which is kind of important. It does happen a lot in practice, but it's a drawback, but sometimes it's what you have to deal with in reality. The ideas behind two-way ANOVA extend to higher order models. We can do three-way or more. A general linear model is a versatile tool for handling any ANOVA model. It handles data that's not balanced, equal variance assumption being violated, three-way interactions, and higher. The statistical design of experiments is an efficient procedure for planning experiments so that the data obtained can be analyzed to yield valid and objective conclusions. There are whole courses that are offered on design of experiments, and they just give you the tip of the iceberg. I would consult a statistical expert if you're in charge of an important study. When there are k factors, each with 2 levels, we have what we call a 2 to the k factorial design. This is useful when the number of factors is large. Even continuous variables can be dichotomized into 2 levels, like low and high, of roughly equal groups. A fully crossed or full factorial design, we've already talked about this, is one that includes all possible combinations of factor levels. A fractional factorial design limits the data collection to a subset of possible factor combinations. An automobile manufacturer studying 10 factors for emissions, each with 2 levels, yields 2 to the 10th or 1,024 possible combinations. So use a fractional design if you're in this situation. If all levels of one factor are contained inside another, the design is called nested. The nested variable cannot be studied as a main effect because it's inside of another effect. In a fixed effects model, the levels of each factor are predetermined. These are the models we're working with. For example, a firm has 3 paint suppliers, so these are the 3 factor levels. In a random effects model, factor levels are chosen at random from population of possible factor levels. Example, a firm has 20 paint suppliers but only wants to study 3, so you randomly choose 3. Random effects models are more complicated to compute and interpret. Consult an expert or study before trying. And always remember, as a student at the University of South Carolina, you can consult with a statistical consulting lab over in the statistics department for free. There's the website for your reference.